So good morning, good afternoon, good evening, wherever you are in the world. Today we have Professor Edward Witten from the IAS in our Matrix online seminar. It's 10 a.m. in Melbourne and 8 p.m. in New Jersey, and so we're very pleased that Professor Witten has given his time to present here. Edward Witten doesn't need a lot of introduction. He's a very productive and influential mathematical and theoretical physicist with profound impact on mathematics, as you all know. So without further ado, I'd like to hand over to Edward. One thing of note, if you have any questions, we'll address them at the end. Please use the Q&A function at the bottom of your screen to type in your questions, and then we'll go through them at the end of the talk. Edward, over to you.
Well, thanks so much for the introduction to give this talk and for the kind remarks. So I'm giving this lecture partly in honor in memory and honor of Von Jones. I better do this before I try talking. Okay. Am I sharing the screen now? Can you see it?
Yes, we can.
Okay, all right. So shortly before the pandemic, I was at a meeting in New Zealand where I had the opportunity to see Von Jones at more length than I had for some time before. And unfortunately, that was the last time, as we all know. So as I said, this talk is partly in honor and memory of Von Jones. So I'm going to be discussing the relations between a sequence of theories in dimensions ranging from 2 to 5. So there will be the conformal blocks of the WZW model, and then in 2 dimensions. In 3 dimensions, we'll have the Jones polynomial and Chern-Simons gauge theory. In 4 dimensions, we'll have Super-Yang-Mills theory. And finally, there will be a dimension 5 construction that leads to a categorification of the Jones polynomial, a candidate for Khovanov homology. So the Jones polynomial, which is no doubt well known to many of you, is a rather subtle invariant of a knot in R3. I've drawn a knot, although it takes a little doing to figure out if it's a knot or a link with more than one component. And Jones gave several constructions of his polynomial back in the 1980s, and many more have been discovered since then. And ever since his original work, which involved temporally Lieb algebras and related things, constructions of the Jones polynomial have generally been related to mathematical physics in a bewildering variety of ways. Jones began, more or less, with the Jones representations of the braid group. So a braid in the mathematical sense is a picture like I've drawn, where some points in the plane are moving around in time, and then possibly returning to their starting positions to make a closed braid. In this example, I drew a braid with 4 strands. Braids form a group. They can be composed by gluing one braid on top of another. And Jones constructed some rather mysterious representations of the braid group, which were relatively simple to define, but had remarkable properties. The representation matrices depend on a complex parameter that's usually called Q. So I'll call these representations R sub I of Q, where I labels the different choices of representation. So one of Jones's original definitions of the Jones polynomial was as follows. You can build a knot by gluing together the top and bottom ends of a braid. The gluing is a little bit like taking a trace. So now if B is a braid, and if R sub IQ of B is the matrix that represents the braid in the representation Ri of Q, then I think even Jones's first definition of the Jones polynomial was that it's a certain linear combination of these traces. So everything about this formula was a bit mysterious. First, the motivation for the specific braid group representations Ri of Q was non-obvious, even though they were relatively simple to define. The particular functions Ci of Q that you need were obscure. But what I think was most obscure was this. Since the same knot can be constructed by taking the trace of many different braids, it's not obvious why you should expect to be able to make a knot invariant in such a fashion anyway. I first learned about these things from Michael Atiyah a couple years later, a couple years after Jones's original work, by which time Jones and many others had extended it quite a lot. Atiyah predicted that the mysteries should be unraveled by interpreting the Jones polynomial in quantum field theory. A very important step in this direction was taken by Tsuchiya and Kanya, perhaps in 1987. They reinterpreted the Jones representations of the braid group as the ones that arise when correlation functions of a two-dimensional conformal field theory called the WZW model are decomposed holomorphically as originally analyzed by Knizhnik and Zamolodchikov. So I won't go into a lot of details here, but briefly, the WZW model is a two-dimensional conformal field theory. It depends on the choice of a compact symmetry group G, and a positive integer K. It turns out that in the relation to the Jones polynomial, G is SU2, and K is related to Jones's variable Q in this fashion. The WZW model has primary fields in various representations of G. To make contact with the Jones representations of the braid group, we'll consider a primary field phi in the two-dimensional representation. So then we consider what are called the correlation functions of this field on a Riemann surface of genus 0, a two-sphere as I've drawn it. The correlation functions depend on the choice of points on the two-sphere. 5 of them in the picture, but in general, n of them. Now, these correlators are neither holomorphic nor anti-holomorphic. They can't be factored as the product of a holomorphic and an anti-holomorphic function. But Knizhnik and Zamolodchikov had shown that there are finite sums of products of holomorphic and anti-holomorphic functions. So here are the functions that appear F alpha are multi-valued holomorphic functions. Under monodromies, the F alphas are transformed to linear combinations of themselves, but in such a way that the matrices are unitary. So the sum of F alpha bar is monodromy invariant. In fact, those are the single valued correlation functions of the model. So for each n, you can define a vector bundle over the configuration space of n points with the bases given by the F alphas. And these are automatically flat vector bundles with the F alpha understood as covariantly constant sections. And their monodromies give representations of the braid group. So what Tsuchiya and Kanya discovered was that these are the Jones representations. So for me, that was very important because it brought the Jones representations into a world that I was more familiar with. As understood by physicists at the time, the WZW model is a purely two-dimensional quantum field theory with no particular relation to 3 dimensions. But the relation of the conformal blocks to the Jones representations of the braid group showed that somehow the model is related to 3 dimensions. There was another clue in that direction from work in this period by Eric Verlinde. Also, there was important work by Greg Moore and Nathan Seiberg. Unfortunately, there isn't time today to recall those matters. Now, in 3 dimensions, there actually is a quantum field theory that depends on precisely the same data as the 2-dimensional WZW model, namely a gauge group G and a non-zero integer K. We simply do Yang-Mills theory in 3 space-time dimensions, with G now regarded as the gauge group, and I'll write A for a connection, or in physical language, a gauge field. But we choose the action to be not the usual Yang-Mills action, but instead to be the Chern-Simons function. So W is an oriented 3-manifold, and this is the Chern-Simons function of a connection. Now, the function I is only gauge invariant modulo 2 pi times k, the way I've normalized it. According to Feynman, the action must be gauge invariant mod 2 pi times an integer, so that the argument of the Feynman path integral, which is the exponential of the action times the square root of -1, will be well defined. So k has to be an integer. That argument, due originally to Deser et al., is somewhat similar to the argument showing integrality of k in the 2-dimensional model that is related to the braid group representations. Now, the importance of using the Chern-Simons function and not a standard Yang-Mills action is that the definition made no use of a Riemannian metric on the 3-manifold W. In fact, it used no structure of W except an orientation. So on an oriented 3-manifold with no additional structure, formally, the Feynman path integral of the theory doesn't depend on anything at all except W itself. In other words, if it makes sense at all, it will give a topological invariant of W. That proves to be the case with one slight emendation, which is that W should be viewed as a framed three-manifold. When you treat this more carefully than we'll have time to discuss today, quantum mechanically. Now we can include a knot or an embedded circle K in W by including what physicists call a Wilson loop operator. That's simply the trace of the holonomy of the connection around the knot K in some representation R. This is the way physicists write the holonomy. So I've just written the trace of the holonomy. And that's a function of connections. We could include it as an extra factor in the path integral. And then the path integral depends on the knot K and the representation R, as well as the three-manifold W, but nothing else. So just taking W to be R3, this will potentially give an invariant of a knot. Now, the basic relation between 3D Chern-Simons theory and 2D WZW model is that the space of physical states of the 3D theory is the space of conformal blocks of the 2D theory. In other words, the space of physical states is what Tsuchiya and Kanya had related to the Jones representations of the braid group. So for example, well, in a quantum field theory, usually we formulate it on a spatial manifold times time, and then we want to construct a Hilbert space of physical states for the theory formulated on that spatial manifold. So here I'll take the spatial manifold to be an oriented two manifold of genus G. So the three manifold is simply that times time. So here I've sketched for genus 2 our initial value surface. Then to construct the physical Hilbert space, we have to quantize the appropriate classical phase space. So in this case, in general, the classical phase space of any theory is the space of classical solutions on some initial value surface times time. In this particular case, since the classical field equation is just that the curvature vanishes, the classical phase space is the moduli space of flat connections on sigma times R, but that's just the same as the moduli space of flat G bundles on sigma. This can then be quantized by picking a complex structure on sigma, which induces a Kähler structure on the moduli space. And then you find that the pre-quantum line bundle for the quantization is the power of the fundamental homomorphic line bundle, sometimes called the determinant line bundle. And the physical Hilbert space is the space of homomorphic sections of this line bundle over the parameter space. Now, I've drastically shortened what's actually a long story, but the point is that the answer that we get coincides with what was then a known and, in a sense, standard description of the space of WZW conformal blocks. It wasn't that well known among physicists. I was lucky to have had it explained to me by Graham Siegel, I believe. Nowadays, essentially, this description in a more general form is widely used in the geometric Langlands program. There probably are some other areas of research where it's well known. I think even today, this description of the space of conformal blocks is not well known among physicists. Anyway, that's the basic link between 2 and 3 dimensions. The Jones representations of the braid groups correspond to the physical states of the three-dimensional theory. Now, to get the Jones representations of the braid groups, we have to include knots, which I omitted in my very brief explanation of the quantization. So we repeat the story that I just explained in the presence of parallel strands that run in the time direction. So it's really quantizing in that generality that we get the Jones representations. And with some further arguments, you can get a formula for the expectation value of the Wilson operator associated to a knot that coincides precisely with Jones's original formula for the Jones polynomial in terms of traces. So that's a very brief explanation of a reinterpretation of the Jones polynomial in three-dimensional gauge theory. I've possibly rushed through it a little bit because I wanted to tell you about a more recent story in 4 and 5 dimensions. In this presentation, the theory is really only defined for an integer k, or in other words, it's only defined for q of this form. Now, if you want a theory that's defined on an arbitrary three-manifold W, that's the right answer. In other words, as far as is understood, the three manifold invariants you can make from this theory are only defined for integer k. But if you're considering knots in R3, then what you get this way can be analytically continued to a function of a complex variable q. In fact, that's where Jones started, after all. It's called the Jones polynomial because J of q is a Laurent polynomial in q. And Jones was not particularly interested in these values. It was discovered later that his representations have special properties of these values. But Jones's discussion made sense as a function of a complex variable. So J of q and its representations, for its generalizations for other groups and representations is a Laurent polynomial. And that's why the Jones invariant and its analogs, generalizations for other cases, are described as not polynomials. Now, from the point of view of the 3D gauge theory, that's mysterious, although the interpretation, well, most other definitions of the Jones polynomial, including the one by two-dimensional conformal blocks, makes it more clear. It follows from simple properties of the Knižik-Zamolodchikov analysis of those conformal blocks. That last statement was part of the starting point of Tucci and Kanya, who made contact between Knižnik and Zamolodchikov and Jones. Anyway, this approach makes topological invariance of the Jones polynomial clear, at least for physicists, but it does not seem to directly explain why the invariants are a polynomial. So this bothered me, but there wasn't much I could do about it. I'm not being able to make any progress in getting an explanation that would simultaneously explain topological invariance and the polynomial nature of the invariance. I moved on and did other things for about 20 years. But by about 2008, there were new developments, among others involving what's called the volume conjecture, that motivated me to look for a new explanation of why the Chern-Simons path integral that I used to describe knots in R3 can be analytically continued away from integer k. So I won't explain what the volume conjecture was in detail, but I do want to remark that my work did not lead to a physics-based explanation of it, which in my opinion is still absent. So I learned, there's been a lot of interesting work by physicists, and I learned a lot from Gukov in particular, whose contributions were what got me interested in the volume conjecture. But I don't think why it's true has a satisfactory physics-based explanation, nor a math proof as far as I know, up to now. But in trying to just understand how you could sensibly interpret the volume, state the volume conjecture, never mind prove it, as a statement about quantum field theory, it turns out that this involves a link between 3 and 4 dimensions that I think is just as interesting as the link between 2 and 3 dimensions. I kind of rushed through the 2 and 3 dimensional story because I wanted to spend more time to explain the more recent development linking 3 and 4 dimensions. Now, before tackling path integrals, so our question will involve analytic continuation of path integrals away from where they are naturally defined. But we're going to practice first with ordinary integrals. So for example, I've written a one-dimensional integral there with a real variable x. But to improve the analogy between this integral and a Feynman path integral, I'm going to derive a differential equation, which in the context of quantum field theory would be called a Ward identity, where Ward, incidentally, I believe, was an Australian physicist, John Ward, who made many important contributions in the early days of quantum field theory and the weak interactions. So from this fact here, we can deduce a differential equation obeyed by the function z of a. So when we generalize the path integral, we want to preserve the Ward identity, which means in this example that we want to preserve the differential equation. So to generalize the original integral, we analytically continue from x to a complex variable z. Then we can write the original integral like so, where gamma is an integration cycle that happens to be the real axis. Well, now we're going to generalize the integral by considering some other gamma in the same integral. Well, what sort of gamma can we use? A closed cycle is no use because the integral will vanish by Cauchy's theorem. Nor can we let gamma have a boundary, for then the Ward identity, whose proof involved integration by parts, will fail. So the only option is for gamma to run from infinity to infinity in such a way that the integral converges. So I've drawn here a couple of examples of possible contours. The integral we started with is convergent along the positive or negative x and y axis. So any contour that starts at the positive or negative x or y axis and ends at another one of those is okay. For example, the x-axis was okay, the y-axis was okay, and these two contours here are also okay. So any one of those contours will lead to another definition of the original integral, such that the differential equation is obeyed. Now, I presented this in one dimension, but it should be clear we can treat an n-dimensional integral with a suitable polynomial f in much the same way. F is to start with the polynomial such that the integral on the real locus converges. Then we analytically continue to complex variable z, and we want to consider an integral over a suitable cycle gamma, which will be chosen so that, well, it should have two properties. Gamma has to be middle dimensional because we're trying to integrate a middle dimensional. See, in the real sense, this was a top degree differential form, but in the complex sense, it's a middle dimensional differential form. So the cycle gamma has to be middle dimensional, and it has to be such that the function h, the minus the real part of f, has to go to minus infinity along gamma, so that the integral over gamma will converge. So for every such gamma, I think I messed up explaining this, but anyway, it's obvious that gamma will be some kind of non-compact cycle. A compact one will give 0, so it's a non-compact cycle, and it's highly constrained by the fact that the integral has to converge. So the real part of the exponent goes to minus infinity at infinity along the cycle. So for every such gamma, we get a generalization of the original integral such that all the order densities, in other words, all differential equations we could have proved involving the coefficients of the polynomial f, will be satisfied. Now, it turns out, though I won't explain all the details today, that there's a nice theory of the possible gammas given by Morse theory. So you do Morse theory with h as the Morse function, and it gives you a good framework for understanding analytic continuation of such integrals. So what we want to do today is to place the Chern-Simons path integral in the same framework. And then we'll analytically continue it away from where it starts, which was integer k. Now, the Chern-Simons path integral starts life as an integral over the infinite dimensional space of all gauge fields A for the compact gauge group G. So these are real gauge fields, or if you like, unitary gauge fields of a compact group. The integrand is the exponential of a polynomial. So we're in roughly the situation I described. There's no problem formally in analytic continuation of the integrand. We just replace the gauge group by its complexification, G sub c, and we replace A by a complex valued connection, curly A, whose real part is A, but it also has an imaginary part. And so, for example, we replace SU2 by SL2C, and the exponent in the path integral is a polynomial in A that we analytically continue to the same polynomial in curly A. And then we replace U by its complexification, which is the space U sub C of complex valued connections. The only catch is that the integration has to run over a middle dimensional subspace gamma in the space of complex valued connections. So we need to find a subspace of the infinite dimensional space of connections that has two properties. One, it should be middle dimensional, and two, it should have the property that the analytically continued path integral converges. How are we supposed to do that? Well, there's a standard way to handle the first part. So we let U sub C be any set of fields on a manifold W. In our application, U sub C is a space of connections, but we could be more general. Then we pick a manifold X of one dimension higher whose boundary is W. So W is our 3 manifold, and we pick a 4 manifold X of boundary W. Then we pick, roughly speaking, any elliptic differential equation on X such that the desired fields on W give local boundary values for a solution of those equations. And we define gamma to be the subspace of fields on W that are boundary values of global solutions on X. This subspace is always within a finite dimensional amount of being middle dimensional, with the difference given by an index of the linearization of this elliptic operator. So if the index is 0, we're fine. If the index isn't 0, we have to make a finite dimensional correction. I'll give an example of this because the description may have been abstract. Suppose we're working on a circle, W, and with a complex valued scalar field phi, and U sub C is the space of complex valued scalar fields on a circle. So one middle dimensional cycle would be to say that phi should be real, but that's rather boring. Here's another one that I'll first describe by hand. Make a Fourier expansion of phi and define a middle dimensional cycle by setting to 0 half of the Fourier components. Well, you might worry that because there's an exceptional one at 0, that this isn't quite middle dimensional, but it's obviously pretty close. But we could put it in our picture. We regard the circle W as the boundary of a unit disk X in the complex Z-plane, where Z is R e to the I theta. Theta is an angle in the circle. So this is the picture. The circle is now the boundary of a disk. And we regard the scalar field phi on W as boundary values of a scalar field on X, which we also call phi. And the elliptic equation we pick is the Cauchy-Riemann equation, that phi should be holomorphic in the disk. The general solution, a general holomorphic function on the disk has an expansion like so. And when restricted to z equals 1, it has a Fourier series with only the non-negative coefficients. So in other words, the middle dimensional subspace that we define by hand is the space of boundary values of solutions on X. That's the general story. Boundary values of fields that extend over X as solutions of some elliptic equation will always be close to being a middle dimensional cycle of fields on W. So going back to our problem with the complex valued connection, A plus I phi on a 3-manifold W, we now set W to be the boundary of a 4-manifold X. On an X, we consider some differential equation, which is supposed to be elliptic. And more or less any elliptic P will do if all we want is a middle dimensional subspace in the space of complex valued gauge fields. But P is essentially uniquely determined if we want the path integral to converge, which was our second condition. See, just as in the one-dimensional example we started with, the path integral is in danger of diverging. Well, even for real fields, the convergence is delicate because it was an oscillatory integral. It was the exponential of I times a real polynomial. But after analytic continuation, the exponent has a real part that's unbounded above and below. So the path integral is in danger of diverging badly. And there's an essentially unique P that will do. What saves the day is that there's an elliptic operator P. So that the integral over X of trace P squared, I left out the trace, plus this thing here, is the dangerous function, the real part of the integrand. So there is a P that makes this true, and it's essentially unique. So the identity says that the dangerous left-hand side is not negative in general, but it's negative when P is 0, which is what we need. So in other words, this identity says that on a cycle defined by the condition P equals 0, the real part of the integrand is negative. So that's the P which makes this identity true is the one that we have to use. Now, glancing back at the last slide, a quantum field theorist might notice something. The negative term that appeared here is actually closely related to the bosonic part of the action of n equals 4 super Yang-Mills theory in a topologically twisted version. And related to this, the equation P equals 0, which in more detail reads like so. For this epsilon symbol is a physicist's way to write the Hodge star. These are equations of localization for a twisted version of n equals 4 super Yang-Mills, which Anton Kapustin and I had actually used in unrelated work on gauge, or a priori unrelated work that until getting to exactly what I'm telling you right now, I didn't realize was related. In our work of a few years before on gauge theory applied to geometric Langlands, we had made use of precisely these equations. Now, we'll soon see why this is useful, but for the moment, let's leave aside the relation to Super-Yang-Mills theory. But the picture is as follows. W is a closed-oriented three-manifold. For any choice of a four-manifold X of boundary W, we get an integration cycle for an analytically continued version of the Chern-Simons path integral on W. The integration cycle consists of all complex gauge fields A on W that are boundary values of a solution of the equation P equals 0 on X. Now, for an integration cycle of this kind, there's never any integrality condition. So I want to give a one-dimensional prototype of what's happened. So Bessel defined this integral for integer k. And this is a function of an integer k and a complex variable t that's got very nice properties as long as k is an integer. However, if you're willing to give up some of its nice properties, you can continue away from integer values of k by changing from the unit circle to another cycle. So one property the left-hand side has is that it's an entire function of t. That's manifest in this definition. I'm about to change to a different cycle where k doesn't have to be an integer, but will no longer get an entire function. You simply replace the unit circle by the contour gamma in the complex z-plane that's drawn, and then as long as t has a real part, I think, of the right sign, which looks like it should be positive, this integral converges on gamma. And so this is an example of continuing an ordinary integral that's naturally defined for integer values to complex values at the cost of losing some of its properties. So, I mean, k doesn't have to be an integer, but now t has a positive real part. And you can continue away from that, but you won't get an entire function. Now, here, when we change the integration cycle, we're going to get a different answer in general, and some of its properties will be lost. But for the special case of knots in R3, you can argue using Morse theory that all integration cycles are equivalent. So the standard integration cycle of Chern-Simons theory can be replaced by one defined this way, for which k has no reason to be an integer. So that gives us a new explanation of why the Jones polynomial can be analytically continued away from integer values of k. In fact, though, because of the relation to Super-Yang-Mills theory, we get much more. The equation P equals 0 is an equation of supersymmetric localization, as it's called, for this supersymmetric Yang-Mills theory in 4 dimensions. In other words, the theory has a particular supercharge Q whose square is 0, such that if we pass through the cohomology of Q, the Feynman path integral of the 4-dimensional gauge theory localizes on these solutions of P equals 0. So this localization, well, it has many analogs in mathematics. One of them is Dorstemann-Ekman-Atiyah-Butt localization of certain integrals on a symplectic manifold, where, for example, if you have a symplectic manifold with a circle action, the exponential of the moment map can be computed by localization at fixed points. One way to prove that is quite similar to this argument in the quantum field theory context. So using this relation to Super-Yang-Mills theory, originally I just stated the analytic continuation of the Chern-Simons theory in terms of this picture, but because of the prior experience with this equation P equals 0, and because of this interpretation, I understood eventually that you can say the following. Let X be a 4-manifold with boundary W. Assuming, well, if X is flat, we could study the physical supersymmetric Yang-Mills theory on X, but even if it isn't flat, you can pick some particular couplings to preserve the supercharge Q, and also you'd pick a particular boundary condition along W that preserves the Q supersymmetry. With this done, The statement is that n equals 4 superangles theory on X gives an analytically continued version of Chern-Simons theory on W. An analytically continued version where the parameter K doesn't have to be an integer. So, okay, in terms of my original motivation, at least it was easier now to state the volume conjecture, although as I've told you, I did not discover any, even at a physical level of rigor, did not find any explanation of why it would be true. But it did lead to something else interesting involving knots and a relation to Khovanov homology in 5 dimensions. So, first of all, the boundary condition that you need to make this story work is one that was familiar in string theory. It arises from a particular system that string theorists have studied a lot, a particular system of branes with a non-zero theta angle. It's actually, though, a rather unusual boundary condition from a topological field theory point of view. From the point of view of the second-order Yang-Mills equations of the bulk 4-dimensional theory, it looks like an ordinary elliptic boundary conditions. But in the theory localized on solutions of p equals 0, the boundary condition is trivial. It just says that p is 0 along the boundary. So in the twisted topological field theory, this boundary condition looks quite unfamiliar. It has an analog in dimension 2 that's related to the coisotropic branes of Kapustin and Orlov and can be used for an analytic continuation of the Feynman integral of ordinary quantum mechanics. But still, it's unusual. Now, the step of going from 3 to 4 dimensions is relatively non-standard because it involves this crazy boundary condition on the 3-dimensional theory, in the 4-dimensional theory, and a rather unexpected link of Chern-Simons in 3 dimensions to super-Yang-Mills in 4 dimensions. But once we get this far, we can get farther using more standard arguments. First, we apply electric magnetic duality to the 4-dimensional n equals 4 theory. In terms of branes, this just changes the brane configuration that is much studied to a different brane configuration that's also much studied. And these brane configurations have subtle properties, but by the time I was doing this work, those properties were pretty well known. So in terms of gauge theory, what this electromagnetic duality does is the following. First, the gauge group G is mapped to the Langlands GNO dual group G dual. Secondly, the parameter Q of the Jones polynomial is related to e to the I theta, where theta is the gauge theory theta angle. That means that a field of instanton number n is going to be weighted by e to the I n theta times q to the n. So actually, part of Atiyah's vision for the Jones polynomial back in the 80s had been that the Jones parameter q would count instantons. That wasn't true in the 3-dimensional version of the theory, but it is true in the version I'm in the process of telling you about right now. In terms of the bulk localization equations, nothing happens. Localization is still on solutions of the same equation. But because of the flip, the boundary condition is completely different. It determines an elliptic boundary condition, but an unusual one, on the equation p equals 0. Because the equation and boundary condition are elliptic, it makes sense modulo compactness issues, which have still not been fully settled. So Cliff Talbs has done a lot of work on these. And his lecture in New Zealand actually made it sound like it might be close to resolution, but that hasn't appeared yet. Anyway, modulo compactness questions, because everything is elliptic, it makes sense to count modulo signs, to count with signs, I should say, the solutions of the equation p equals 0. That satisfy the boundary condition. So if an is the number of solutions of p equals 0 with instanton number n that satisfy the boundary condition, then supersymmetric localization says that the partition function, first of all, is a Laurent polynomial, and then the prediction is that this is a dual formula for the Jones polynomial. So to make this true, first of all, W should be R3. I drew it as if it's something else. I drew a compact W because it's easier to draw. But to literally get this statement, we work on R3 times a half line That's a very simple four manifold with boundary. And the boundary condition is a rather complicated story, but in particular, the boundary condition depends on the knot, which lives in the boundary. And the claim that comes out of this story, and I've cut some corners, so I haven't certainly explained everything, is that the counting, see, for every value n of the instanton number, you count solutions with signs and get an invariant an. It's a kind of analog for this problem of the Donaldson invariance of four manifolds. And then the sum of an q to the n is supposed to be the Jones polynomial. So this is finally supposed to be what didn't come from Chern-Simons in 3 dimensions, but comes from many other approaches to the Jones polynomial. Now there's a gauge theory approach in 4 dimensions that gives a natural explanation of why the Jones polynomial is a polynomial, or at least it would once the compactness issues are settled. Now, I think the last, the boundary condition on the equation p equals 0 that we need here has all the general properties of an elliptic boundary condition, but it's constructed in an unusual way by requiring the fields to have a certain sort of singularity along the boundary. So with Rafe Mazio, I actually wrote 2 papers on this boundary condition, and Cliff has also re-examined it from his point of view. So it's too long to explain the boundary condition in full, but I'll give you a taste. You pick coordinates x along the boundary and pick a coordinate y normal to the boundary. So the boundary is at y equals 0. And then phi is a 1 form valued in the gauge group. It's the imaginary part of the connection. I expand it in the basis of 1 forms dy and dx. And the boundary condition is defined by requiring phi to have what I call a non-pole. So you pick T as standard generators of the Lie algebra of SU2. And phi has a 1 over y singularity as y goes to 0, where T are a standard set of SU2 generators. So this is a singular solution of the equation p equals 0. It's a solution of the equation p equals 0 that has a certain prescribed singularity on the boundary. And the claim is that requiring, more familiar or more standard boundary conditions like Dirichlet or Neumann, something vanishes on the boundary or has a prescribed value on the boundary, or something has a vanishing normal derivative on the boundary or something like that. Instead of prescribing the value on the boundary, here we prescribe a certain singular behavior along the boundary. But you can show that it has all the properties of a standard elliptic boundary condition. So, however, I only described the boundary condition to you without a knot. With a knot, there's a more complicated story. So with a knot, the singularity looks like this away from the knot, and then there's a more complicated description of the singular behavior of the fields along the knot. Finally, from this starting point, you can categorify the Jones polynomial and get a candidate for the Khovanov homology of a knot. What we get is closely related to work of Gukov, Schwartz, and Waffe, who were the first physicists to explore Khovanov homology from a physics point of view. There's also somewhat related perspective in recent work of Mina Aganagic, this paper and a more recent one that, which I haven't cited here. Now, in terms of branes, categorification means replacing the D3, D5 system by a D4, D6 system. So, starting with D3 branes on a 4 manifold X, you go to X times a circle, and then you decompactify to X times R. The first step does nothing from a point of view of topology, but the second step is categorification. It means that you construct a physical Hilbert space, the space of, as I said earlier in discussing Chern-Simons theory, you formulate a theory on R times something and construct a space of physical states associated to the something. Here, the physical Hilbert space associated to X is the candidate for Khovanov homology. H is Z times Z graded by instanton number and a certain fermion number, which is an Atiyah-Petrosinger eta invariant. And if you decompactify, you can decategorify, as in Khovanov's work, you can decategorify by taking a Lefschetz number, so to speak, or an index, whatever you want to call it. by taking this kind of function in the graded Hilbert space, you can recover the Jones polynomial. Now, okay. To explain it to physicists, I would talk about this brane construction, but to briefly explain it without mentioning branes, we can do the following. Remember, the Jones polynomial comes from counting solutions of an equation. In general, you can't categorify the set of solutions of an equation, as far as I know. But according to Morse theory, the set of critical points of a function can be categorified. The categorification of the set of solutions of the equation df equals 0 is the cohomology of the manifold M. So we want the set of solutions of the equation p equals 0 to be the critical points of some functional. That's actually not true in a generic form manifold, but it's true for a form manifold of the special form W times R plus, which we use in studying the Jones polynomial, and it can be generalized a little bit. If somebody tells you that this equation on this kind of form manifold is the equation for the critical point of something, it's not too hard to find what the something is. But if you don't have a reason to think it's true, you might not go looking for it. I was looking for it because I knew Khovanov homology existed, and I was trying to figure out what could possibly give an explanation of Khovanov homology from this point of view. So my assertion is that for this kind of X, the equation p equals 0 is the equation for a critical point of some gamma. Well, I hope I've written what gamma is. It looks like I haven't. Maybe I'll do it in the question period. But anyway, gamma is a simple formula in terms of the curvature of the connection and also this one form phi. Categorification means that you add another dimension, replacing x by x times r, which I'll call y. R is parameterized by the time, and then you introduce the gradient flow equation. In ordinary Morse theory, you start in 0 dimensions, as a physicist would put it. You just had a finite dimensional manifold. Then you look at gradient flow, which means you introduce a time direction. So in Morse theory, you'd be going from 0 to 1 dimension, but here we go from x to x times r, from 4 to 5 dimensions. And one more lucky thing happens. If you take a generic gamma, which is a function of fields in 4 or any other number of dimensions bigger than 0, a corresponding gradient flow equation will not be elliptic in 1 dimension more. I only know a few cases in different dimensions of functionals where the gradient flow equation actually is elliptic. And I think those examples are all interesting and important. This is such an example. So this 5-dimensional equation is an elliptic equation, so it makes sense to count its solutions. And assuming the relevant compactness issues are overcome so that you can do this counting, you can construct an analog of Floor cohomology, and this is the categorification of the Jones polynomial from this point of view. Concretely, it means the following. The solutions of p equals 0 are the classical vacua. You make a Hilbert space H0 with one basis vector for each classical vacuum. The incident number and fermion number, or eta invariant, are two integers, n and f, associated to a classical solution. So that gives a z times z grading of this Hilbert space. The physical Hilbert space, which is an invariant of the knot, is not H0. Rather, it's the cohomology of a certain differential, or physically, it would be called a supercharge, that acts on H0. The matrix elements of the supercharge or differential between different basis vectors are computed by counting the gradient flow lines between different critical points, as in the supersymmetric approach to Morse theory. Now, to summarize what I've told you, and I apologize for perhaps rushing through it too much, we've discussed the relations between a chain of theories in dimensions 2, 3, 4, and 5. In dimension 2, we have the conformal blocks of the WZW model of conformal field theory. In dimension 3, there's the Jones polynomial and its description by Chern-Simons theory. In dimension 4, we relate this to n equals 4 super Yang-Mills theory. And in what I assume is the last step, but let's make no promises, we go to dimension 5 and get a categorification of the Jones polynomial. Thank you.
Well, thanks very much. I'll applaud on behalf of everyone. Thanks also for your attribution to Vaughan Jones, who indeed passed away too early. So for those attending, questions can be put in the Q&A function at the bottom of your screen, and we'll go through them now. So maybe I'll start with the first question. Is there a mathematical proof of 3D Chern-Simons and 2D Witten having the same physical Hilbert space?
Well, there can't be, because there isn't a mathematical proof of there isn't a proper mathematical proof of Chern-Simons existing as a quantum field theory. That's mathematically, that's an unsolved problem. As for the statement, they have the same Hilbert space. Quantization of Chern-Simons theory leads to this space of holomorphic sections. And I think, yes, there is a mathematical proof that those are the conformal blocks of the WZW model. For example, as I said during the lecture, to people working on geometric Langlands, that's a basic fact. Not everything about the WZW model is mathematically rigorous, but a lot is. To physicists, what physicists view as some of the most interesting questions about the WZW model are not mathematically rigorous, but still a lot is.
Right. So the next question is, does the point of view you gave give insight into the volume conjecture?
As I said in the lecture, I did not arrive at any understanding of why it's true. All I learned was that I could reformulate the volume conjecture. I could find an integer invariant such that the volume of a knot, such that the volume conjecture is true for a given knot if and only if that invariant is non-zero. But I have no idea why it would be true that that invariant is non-zero for all knots. For all I know, you could find a crazy knot with 78 crossings, and the invariant would turn out to be 0. If there's a reason that the volume conjecture is true for all knots, I definitely didn't discover it.
Okay. So please keep submitting your questions through Q&A is another one. In 4D gauge theory, out of ASD Yang-Mills, there are two developments leading to, well, VW and KW equations. Any relations between ASD Yang-Mills, VW, and KW? You may have to explain the deviations here.
Okay. I think it was hard to hear, but VW and KW, they're okay. From supersymmetric gauge theory, you can make twisted versions, localization equations, that give various interesting supersymmetric localization equations, many of which are important mathematically. One is the instanton equation for Yang-Mills instanton field. So since the work of Donaldson, by now more than 35 years ago, it's been clear that that's important mathematically. The second is the Seiberg-Witten equation. It arises in the same way, starting from a slightly different starting points. A slightly different supersymmetric theory in 4 dimensions. The question is about two other elliptic equations in 4 dimensions that both can arise by localization of 4-dimensional supersymmetric equations. One is this equation P equals 0 that occurred in my lecture, and another is an equation that Voff and I studied 25 years ago, which I guess you were calling the VW equation, where we were studying it, originally we were studying it to give, to test what was then a not well-established physical conjecture about electromagnetic duality. That was what we were originally doing. I believe that, well, the KW equation I think is important in connection to this geometric Langland story. I don't know whether the VW equation is important for 4 manifolds. I think the evidence is that that if you take the question literally, it won't be, that you won't get essentially new 4 manifold invariants, even if you can define them. But the VW equation has a categorification formally in 5 dimensions. There's an elliptic PD in 5 dimensions, which is the same one that occurred in my lecture, actually. So I didn't say this because we didn't get it that way. The way I said it was that this equation, some people call it the HW equation. H is for Hades, Andrew Hades. Anyway, we got this equation in 5 dimensions as gradient flow from the P equals 0 equation. But the same equation with a different interpretation, you could be studying any 4 manifold X, and you're trying to you could start with the VW equations on X, and you want to categorify the VW invariants. So for many, many years, my pet idea about where fundamentally new 4 manifold invariants would come from would be by categorifying the VW equation, the VW invariants. Mathematically, there's a lot of trouble making sense of that. And it's not something where physics has gotten much insight. I hope I've answered the question, or at least told you something about the VW equation.
Right, thanks. So the next question was what you anticipated in your talk. Can we see a formula for that gamma 8 phi?
We can if I manage to, well, I'm extremely bad at writing. I'm not set up. Okay, yeah, okay. So there was a Yang-Mills curvature. Now, the field which was the one form in 4 dimensions. So we do something that isn't possible for general 4 manifold. Remember, our 4 manifold was W times R. Sorry. Okay. We're going. Okay. Anyway, I'm going to write a functional for a self-dual 2 form B and the Yang-Mills curvature. The functional is just FB. I'm really not set up to do this very well, but this little bit I'm writing, if you're patient enough, I can do. We take FB minus B cubed, take its trace and integrate it. And, sorry, I'm just trying to put parentheses around FB minus B cubed. That's the functional whose gradient flow, that's the functional whose critical points are those solutions of P equals 0. Not on a general 4 manifold, but on this kind of 4 manifold, W times a 1 manifold. So I told you if you thought it had to be true, it's the functional is simple. You might not look for it if you didn't have a reason to look for it. And in my case, since I knew Khovanov homology existed, there was a motivation to look for that functional, and it exists. And even better, you see, as I said also in the lecture, but I didn't properly explain it. Okay, so what's magical about this functional? Well, what's magical about it is that gradient flow will always be a differential equation in 1 dimension more, but generically it won't be elliptic. Try it at home. Write down a functional and write down the gradient flow equation in 1 dimension more. You'll more often get a parabolic equation than an elliptic one. You can get lots of parabolic equations that way, but good luck finding elliptic equations. If you find one, I recommend to publish it. I think they're all significant.
Okay. So the next question is, you talked about analytically continuing Chern simes away from K integer. Does this have an analog for 2-dimensional CFT, for example, SO2 with Witten?
I think I have to answer yes. So as a unitary quantum field theory, the WCW model has integer K and compact gauge group G. But for example, when Tsuchiya and Kanya studied its conformal blocks, they didn't limit themselves to integer K. The conformal blocks made sense for any K. And the conditional homological equation wasn't limited to integer K, at least in the case of genus 0. So you can do lots of things away from integer K. It doesn't have all the same properties. So for example, people who work in geometric Langlands study all kinds of generalizations of the WZW model. Well, they're so far afield from the WZW model that even to call them generalizations of it is a bit misleading, I think. But anyway, they don't focus on the special case where you get a unitary quantum field theory. So the answer is that everything, okay. I've had trouble answering your question because there are too many different directions in which it's been generalized and analytically continued.
It's a lot to research there then. Another question, can this story be generalized to knots in genus G Riemann surfaces across R?
That's an excellent question. I expect you can do some interesting things there. I'm pretty sure you can get something interesting. The statements might not be as simple. Well, the compactness issues might be more complicated. So when I said I was optimistic that the compactness issues were close to being resolved, that was for knots in R3. And R times CP1 would also be okay. But when you have negative curvature, the compactness issues might be more complicated in an essential way. So technically, I'm not sure what would happen. Formally, it makes perfect sense, what you're asking. Some physicists have done pieces of such generalizations. I haven't myself, and I'm not that well versed in what's been done.
Another question on the VW equations. There seems to be ongoing work of Moore claiming VW equals SW. Do you know of any new progress?
Well, I know Moore's recent paper, if that's what you're asking about. And, well, he had formulas under certain conditions for the Witten invariants, which support the claim that they are not essentially new form manifold invariants. I believe that that's true. As I said in answer to one of the other questions, my dream is that, well, formally those invariants can be categorified using this equation that's here on the screen. I'm not sure I can highlight, but well, the one that I've just messed up with. Using that equation, but viewed differently from the way I presented it in the lecture. Formally, you can use that to categorify the VW invariants. There are serious mathematical difficulties, so I'm not certain if it really works. But there's definitely no physical reason to doubt that it would give essentially new invariants, and I'm optimistic it would. I'm not optimistic about the VW invariants being essentially new.
Mathematically, one can see the role of Langland's dual group in the Jones polynomial story, or its generalization. So can we see that?
The question is, can we see it?
So mathematically, can one see the role of Langland's dual group in the Jones polynomial story, or its generalizations?
Well, my conjecture involved the Langland's dual group. So you take the Jones polynomial for a given group G. Jones and others working in the 80s generalized the Jones polynomial from the original context to an arbitrary compact Lie group G and an arbitrary representation. So that's what I mean by the Jones polynomial for an arbitrary group G. Then I had a dual formula. I'm not sure why I can't go backwards. Okay. Oh. Okay. I had a dual formula for the Jones polynomial. This one that involves counting solutions, and those are solutions for the Langland's dual group. So if you only do the Jones polynomial for SU2, it won't be that striking. The dual group is SO3. It has the same Lie algebra. And in this very simple topology, you won't see much difference between SO3 and SU2. But if one managed to understand this formula for a general Lie group, you'd see that the solutions that you have to, equation you have to solve to get in this formula is for the Langland's dual of the gauge group that appears in the Jones polynomial. I hope I managed to state that clearly. I stumbled a little bit, but perhaps it was clear. You have the Jones polynomial for one group G, and this dual formula involves solving the equations for the Langland's dual group.
Right. Well, thanks very much. We went through all the list of questions. So if there are no further questions, then I'd just like to thank you again, Matt, for giving a wonderful talk. And again, the attribution to Vaughan Jones is very much appreciated for our friends in New Zealand.
Well, thank you very much for the kind words, and also thanks for the invitation to give this lecture.
Yeah, and thanks everyone for attending, and we'll see you again next month in the next installment of the Matrix Online seminar. All right. Bye-bye, everyone.
Bye-bye.